In this video, we're going to start into chapter 6, which is our last chapter. And this video in particular is going to cover section 6.1, which is power series. And so, we've been talking about series. Chapter 5 was all about, okay, can we tell if a series converges or diverges? And now in chapter 6, we're going to start to apply the concept of a series to some different applications. So very first type of series we're going to talk about is a power series. And one of the first things we're going to do is talk about its radius of convergence and interval of convergence. And that'll be what this first video focuses on. And then in the second video, we're going to use what we know to try to make a power series representation for different functions. So real quick, right off the bat, what is the definition of a power series? And it looks a lot like the series we dealt with in chapter 5. The only difference is that now we see x's. X's are involved, right? So before it was always just n, right? Just n, but now we have x. And so it could look like this first form here. So it could have a power series that looks like that. And when we have that, that is what we call a power series centered at x equals 0. And notice that it's always x raised to the n power. So x plus x squared plus x to the third plus x to the fourth. We could also, though, have a power series centered at x equals a. And when we have that, it has a slightly different format. Instead of x to the n, it's x minus that center point to the n. Okay, so there are one of the things that we need to think about then, since we have x involved, and x is a variable, is that the values of x can change. So notice it says here, since the terms in a power series involve the variable x, the series may converge for certain values of x and diverge for other values of x. So we're still concerned about whether or not those series converges or diverges. In fact, we're going to use the test that we learned in chapter 5 to tell that, but it's not necessarily going to converge for all values of x. And there's some theorems and definitions that talk about this. We have a theorem that talks about convergence of a power series. There's basically 3 different ways that a power series can converge or diverge, and we're going to talk about that a little bit more on the next page. I'm not going to really delve into this theorem much. I'll let you read that on your own. We also have this definition which talks about things like the radius of convergence and also the interval of convergence. So, when we're talking about the interval of convergence is just the values of x. This is the values of x. And I don't need to write that, I guess. It says it's the set of all real numbers x. That's the values of x where the series converges. So could be that x only converges, or the series only converges for one value of x, but it could be that it converges for a whole range of values. Like it could converge for all values of x between -3 and 5, okay? Now, if that was the case, if this was our interval of convergence, that would mean the center would have to be at 1. So the center of this interval would have to be x equals 1. And so if you take a look at that interval, right? So here's 0, that's 0, then this is 1, 2, 3, 4, 5. Then we have -1, -2, -3. So look at that, the center being right here. This is the center. What's the radius of that interval? So what's the distance from the center out to each endpoint? So this is r, that's our radius. When we talk about the radius of convergence, that's r. What is that distance for this? Well, it's 4, right? It's 4 from 1 to 5, and it's a distance of 4 from 1 to -3. So those are what we're talking about when we're talking about an interval of convergence and a radius of convergence. In this case, this example, for all values between -3 and 5, that the series is going to converge. If it's any value outside of that interval, it's going to diverge. And so based on that definition and the theorem on the previous page, there are some very important notes that we want to consider. The first note is right here. It says if a series converges for all real numbers x, then we say the radius convergence is r equals infinity. Okay, so that converges for everything. But if a series only converges at its center, say x equals 1, for example, then the radius of convergence is going to be 0 because it only converges right there at the center, so x equals 1. It doesn't converge for any values outside of that, so there is no radius. Radius is 0. And then another thing is the convergence of the endpoints of the interval of convergence is determined individually for every series. So we always need to check the endpoints. We always need to check the endpoints. And we'll show you that in an example here. Okay. Another thing. All series are guaranteed to converge at their center. All power series converge at their center. So say the center is x equals a. Well, if x equals a, and we plug x equals a into our series, then we get a minus a to the n power, a minus a to the n power, and a minus a is 0, so we get 0 to the n power. Well, what do we get if we raise 0 to the n power? Well, it depends on what that power of n is. So if we start at n equals 0, we get c of 0 times 0 raised to the 0. Well, anything raised to the 0 power is 1. So this is going to be c sub 0 times 1. And then if we go to the n equals 1, we get c of 1 times 0 to the 1. 0 to the 1 is 0. So that's going to be c sub 1 times 0. That goes away. And it goes away for all other values of n. So n equals 2 is 0 to the second. That's going to be 0. And so we just end up with C0. Now, that's a constant, right? So what that's saying is that our sum, our power series sum, is C sub 0. In other words, it converges. Series converges. Okay? And then here's kind of a picture of what those different intervals look like. So in the first picture, this only converges at the center. Only converges at the center. X equals a, which means that r is equal to what? There's no interval, so r equals 0. Next one, converges everywhere. Converges everywhere, which means r equals what? R equals infinity. And then the last one converges on some interval. So this one converges, this one converges for the interval x minus r to x plus r. And again, we're going to see this in an example here. So let's jump into example 1. So it says find the radius of convergence and the interval of convergence of the series. Now, one thing I did skip was the 0.5. I just realized. So we're going to use the ratio and the root test almost every time for these types of problems to find the interval of convergence and radius of convergence of a power series. So make sure you remember that. The ratio and the root test are what we're going to use. So let's take a look at an example. Example 1 is going to cover how to find the interval and radius of convergence. And the directions say find the radius of convergence and interval of convergence of the series. And so just to begin with, before we jump into that, let's real quick talk about how we find the center for a problem like this, how we find the center of the interval if there is an interval. And so all you do for that is you take the part that is raised to the nth power that has the x in it. So you just take this and you set it equal to 0. So if we take 4x minus 8 equals 0, that means that 4x is equal to 8, which means x is equal to 2. So x equals 2 is the center of the power series. Is the center of the power series. Okay, so again, remember, if we're going to try to tell if for what values of x the series converges or diverges, we're going to use either the ratio or the root test. And remember, we use the root test only when everything in the series is raised to the nth power, but we just have an n down here in the denominator, which is not raised to the nth power. So we want to use the ratio test. So let's try using the ratio test. We're going to go ahead and find the value of rho, which is a limit, right? Rho equals the limit, the absolute value, and then we're going to have 2 to the n plus 1 times 4x minus 8 to the n plus 1 over n plus 1, and then times n over 2 to the n times 4x minus 8 to the n. That's a nice little review there of the ratio test. And so we now want to go ahead and simplify this. And when we do that, this is stuff we learned from last chapter. So we know that the 2 to the n plus 1 over 2 to the n is going to reduce to just 2. And the same thing with the 4x minus 8 to the n plus 1 over 4x minus 8 to the n. That's just going to leave a 4x minus 8 in the numerator. We also have that leftover n in the numerator, and then on the bottom we have n plus 1. All right, so we're making good progress. Now, here's the thing about our limit. Our limit involves n approaching infinity. So anything in our limit that does not include n can come outside the limit. So that means in this case, we can pull out the 2. We can also pull out the, and notice I don't have 2 in absolute value because absolute value of 2 is 2. Now the 4x minus 8, that needs to remain inside the absolute value because that can go negative depending on the value of x. And then we have times the limit, and what's left is the stuff involving n. So we have n over n plus 1 wrapped in absolute value. All right, so now this is something we should know. What is the limit as n approaches infinity of n over n plus 1? Well, we know this limit approaches 1. So what we're left with is 2 times the absolute value of 4x minus 8. And we can't go really any farther than this, but one thing we do know about the ratio test is the ratio test will only converge when the value of rho, remember this was what rho was, when rho is less than or equal to 1, or not equal to, just less than 1. So let's make a little note of that. The ratio test shows convergence when rho is less than 1. And so we can go ahead and now solve for x. That's where we're going to go now. So we can go ahead and start by dividing by 2. All right, so if we divide by 2, that leaves absolute value of 4x minus 8 is less than 1/2. Divide by 2. And then notice that the 4x minus 8, that both the 4x and the 8 are divisible by 4. So we could actually factor out a 4. And since the absolute value of 4 is 4, we could pull that outside there. So we have 4 times the absolute value of x minus 2 is less than 1/2. And then we could go ahead and, again, trying to get x by itself, we could divide by 4. And when we divide by 4, we then get x minus 2 is less than 1/8. Now, notice again here, we can really see what the center of the power series is because we can see that when x is equal to 2, we get 0 over here inside this absolute value, right? When x equals 2, that's going to become 0. And then one other thing that is significant here is once you get that x minus or x plus or whatever you have inside the absolute value, once you get it to this point, not at the 4x minus 8. So when we were 4x minus 8, there's still a coefficient in front of the x. But once we clear that coefficient in front of the x, then whatever is on the other side is always going to be our r value. So right here, this actually tells us what the radius of convergence is. The radius of convergence is 1/8. We're going to see why here in a second, because if the center is at 2, then, okay, let's wait. Well, before we say that, let's go ahead and rewrite this without the absolute value. So we know from algebra that this inequality can be rewritten like so. And then in order to get x by itself, we need to add 2 everywhere. So we can go ahead and add 2 to all 3 locations. When we add 2 to negative 1/8, so this is 2 minus 1/8, is going to be 15/8. When we add 2 to the middle, we just get x. And when we add 2 to positive 1/8, we get 17/8. So essentially, that's why 1/8 is the radius, because we're taking it and we're adding and subtracting it to our center, which was 2. Remember, this is the center, x equals 2. So the only thing left that we have to do is we have to go ahead and check the endpoints. So we need to check the endpoint of the interval of convergence. And I call the interval of convergence the IOC. So if we check the interval, the endpoints, so the first one we want to check is the left endpoint. That's x equals 15/8. Okay, and this is pretty easy to do. All we do is we take that value of 15/8 and we plug it into the original series. So when we do that, that's going to look like 2 to the n over n times 4 times x minus 8. Well, what is x though? Excuse me, what is x? X is 15/8, so we have 15/8 minus 8 raised to the nth power. And you can do a little bit of simplifying there. When we simplify that, that part inside the n power is going to all reduce down to, you can do the math on your own, but this comes down to negative 1/2 raised to the n. Okay, well that also simplifies because we can apply that n power to both the numerator and denominator for the negative 1/2 to the n. So this can be rewritten as negative 1 to the n over 2 to the n. And then our 2 to the n's will cancel. Hopefully that makes sense. And we're left with very simply a power series that, or a series, not a power series because we don't have x anymore, but a series that is something we've seen before. Do you recognize the series here? This is one of the ones I asked you to memorize. It's almost like the harmonic series, but because of the negative 1 at the end, it alternates. So this is the alternating harmonic series. The alternating harmonic series, which what? Does it converge or diverge? It converges. Very good. All right, so that means that because it converges at x equals 15/8, we need to include that value in our interval. So I can go ahead and put an equal sign here in our interval. This is going to include 15/8. Now let's go ahead and check the other endpoint now. So x equals 17/8. And I would like you to go ahead and try this one on your own. So go ahead and pause the video and see if you can figure out what that's going to come out to. Okay, welcome back. Now, when you go ahead and plug in 17/8 you should get something that comes out to 2 to the n over n times positive 1/2 to the n. And that should simplify then to another series that we're familiar with, 1 over n, which of course is the harmonic series. Which diverges. So our interval will not include 17 over 8. But that does mean that we can go ahead and write our answer, because our answer asks us to find the interval of convergence. So the interval of convergence is going to be 15 over 8 to 17 over 8, not including 17 over 8, so we'll put a parenthesis there. And then our radius of convergence is 1/8. And that's how you do these problems. We got a couple more to look at, but hopefully that all made sense. So in example B, notice we have n factorial times 2x plus 1 to the n. This is another one where we're going to want to use the ratio test. We don't have everything raised to the nth power. We use the ratio test, and we're going to want to find that rho value again. So rho is equal to the limit as n approaches infinity, and we have basically n plus 1 factorial times 2x plus 1 raised to the n plus 1. We're dividing that by n factorial times 2x plus 1 to the n. And so let's go ahead and take this limit. Let's simplify what we have inside the absolute value. We're going to have the n plus 1 factorial over n factorial is going to simplify down to n plus 1. And we know 2x plus 1 to the n plus 1 over 2x plus 1 to the n is just going to leave us with 2x plus 1. And again, we can pull the part out that does not involve the absolute value. That does not involve n. So we can pull the x part out. So we have the absolute value of 2x plus 1 times the limit as n approaches infinity of n plus 1. And if we go ahead and take our limit there, we can now take the limit as n approaches infinity. We know that that limit is going to go to infinity. And so we get absolute value of 2x plus 1 times infinity, which anything times infinity, it doesn't matter what value of x we have here, that whole limit is going to be infinity, right? Anything times infinity is going to be infinity. Now, infinity is always going to be greater than 1. And we know that when rho is greater than 1, a series, according to the ratio test, must diverge. So let's go ahead and make a statement there. So the series diverges everywhere except at the center, which is the value x equals negative 1/2. Now how do we know that? Well, the center always, so to find the center, again, we're just going to take that 2x plus 1 part, and we're going to solve for it. Set it equals 0 and solve for x. So that's going to tell us that x equals negative 1/2. We did that in the last one too, right? Well, we didn't do it that way, but we could have done it that way. We could have taken this, and we could have said 4x minus 8 equals 0, which means 4x equals 8, which means x equals 2. Okay, so this one's only going to diverge. It's going to diverge everywhere. It's only going to converge at x equals negative 1/2. And so our answer here, our interval of convergence, is just the center. It's just x equals negative 1/2, which means our radius of convergence is 0. That's our answer. Okay? Let's do one more example here. This one tells us that our center is x equals 6. Let's go, now notice here we have everything raised to the nth power, so this one we can go ahead and use which test? The root test. And when we use the root test, we're going to find our value of rho by taking the limit as n approaches infinity of what? Do you remember how to do this one? We're going to take the nth root to get rid of those n powers of the absolute value of x minus 6 to the n over n to the n. So that's going to get rid of those nth powers. We're going to get the limit as n approaches infinity, and what's left is the absolute value of x minus 6 over n. Again, pull out the x part, so we have absolute value of x minus 6 times the limit as n approaches infinity of 1 over n. And now we can go ahead and write what that limit equals, right? Because as n approaches infinity, this limit approaches 0. And so anytime if we're going to have absolute value of x minus 6 times 0, that just makes the whole thing 0. And that's 0 is always less than 1. So it doesn't matter what value of x you have here, it will our limit, our rho value will always be 0, which means it will always converge. So what this says is right here, because 0 is less than 1, the series converges for all values of x. Okay, so what does that mean about our interval of convergence? Our interval of convergence is going to, remember, it converges for all values of x. So that means our interval of convergence is negative infinity to positive infinity. And it means our radius must then be infinity. All right. So that's going to do it for this video. You now know how to find the radius of convergence and the interval of convergence for different power series, and we do that using the root test and the ratio test. All right, I'll see you in the next video. We're going to talk about how to represent functions as power series. Thank you.